How's your morning been?
Yeah, it's been good, thanks. How are you?
Pretty good, pretty good. How about you, Soya? How are you?
Yeah, not too bad. What about you?
I'm chilling. I just woke up. Bro, I'm such a bum. Uh, so, how are you, Blessing?
I'm pretty good. I also just wake up not too late.
Okay, amazing call. These guys are incredibly locked in, bro. So, I'm just gonna see if anyone else joins. We might just have the three of us for today. But today we're gonna be covering a little bit of the so let me just screen share this one. So uh, last time we covered so the first thing we did was we did the nomenclature of organic chemistry molecules, how to identify the different homologous series and uh, their different properties. So the various properties behind the different homologous series. Yeah. Today the focus and then yesterday the focus was on understanding the pathways. So we have the major pathways, which are the basic pathways, which are all of the small molecules, so these small hydrocarbons, right, or the small organic molecules. But then we also have the large organic molecules, so that's our amino acids, that's our triglycerides, that's the monosaccharides and the polysaccharides, and how all of those things come together. So from here, we're gonna use some of that knowledge that we learned yesterday in today's lecture for the first part of organic analysis, which is the chemical analysis. Yeah. So the chemical analysis just helps us identify what we may be looking at. It doesn't give us a specific idea of what it might be, but it gives us an idea of what we may be looking at. So might be able to identify this is a carboxylic acid, right? This is a ketone, right? All of the chemical analysis, or the majority of the chemical analysis stuff, focuses on can we identify can we use our understanding of organic pathways to identify what homologous series this is? Yeah. The other thing that we'll be pointing out today is the melting point and the boiling point test, right? So that's going to be steam distillation as well as that melting point test you guys will see, yeah? And then the final thing that we're going to be looking at is going to be titration. So we'll be introducing redox titration. I'm guessing most of you guys are familiar with acid-base, but here we'll be looking at the redox titration stuff. So before we get started, does anyone have any questions, any comments, any concerns? Okay. So let me just pull out this one. So the first thing we have is the bromine water test, yeah? And here we're just adding bromine water to our sample, right? We don't know what the sample is. And here what the bromine water test is, it tells you whether it's saturated or unsaturated, right? If we have a unsaturated compound, what's going to happen is that the solution is going to remain colorless, yeah? What's going to happen here is that the solution remains completely colorless, yeah? Because what's happening is that the why is it drawing so weird? Just clean all this stuff. So what's happening here is that we have we can think about it as an addition reaction, yeah? We have if it's positive, yeah, what's happening here is the alkene is reacting with the bromine to form that dibromoalkene, yeah? Alkane, yeah? So that's what's happening if it's unsaturated. If it's saturated, no reaction is going to happen between those two molecules, yeah? So no reaction is going to happen between those two molecules. So how the bromine water test is, it goes off the addition reaction, right, from yesterday, yeah? If it's a unsaturated compound, basically it doesn't have any double bond, or if it has double bonds or triple bonds, right, it's going to remain completely colorless. But if it doesn't contain double bonds, right, it's going to be the same color as the bromine water. because the bromine hasn't reacted. The bromine's still there, right? Does anyone have any questions about that bromine water test? Give me like thumbs up if that's all chill for you guys, so that makes sense. And if you can't do thumbs up, I don't know, like do a flip or something. Okay. A couple people. Swayam, Blessing, does that make sense for you guys?
Yeah, I'll do a thumbs up.
Okay. It's in the bottom. It's like in the it's like in the
Yeah, I'll
you'll
yeah.
figure it out. You guys are young. Everyone was making fun of me for not knowing how to use technology yesterday. So, I mean, they have this little these are literally the only two definitions they have in the chemical analysis one. It's basically what is a carboxyl group and what is a hydroxyl group. A carboxyl group is what carboxylic acids have, and a hydroxyl group is what something that has a hydroxyl functional group. But it's pretty straightforward. So again, it's just pulling from all the stuff that we knew before. There's nothing like crazy or new here. So here, right? This one is actually this one's here is an oxidation test, yeah? And essentially what's happening here is that we're using one of our oxidizing agents. So here, this one they have is the potassium permanganate test. And what happens here is that if there's a double bond present, so this is another double bond test, yeah? If we have an unsaturated compound, right, or an alkene, yeah, what's going to happen is that when we put this permanganate in, or this potassium permanganate, what's going to happen is that we're going to form this manganese dioxide, yeah? If we don't have any double bonds here, we're just going to there's not going to be any reaction. It's going to be the exact same color as the manganese because it hasn't reacted, yeah? So that one, so those are our two saturated or unsaturated bond tests. That's how we tell unsaturated or saturated bonds apart from one another. Does that make sense for everyone? Okay. Thumbs up all around. Let's go. So here, this is the specific reaction that's going on here. Yeah. Here they've chosen ethene. There's no reason for it to just be ethene. It could be any alkene. Yeah. But they've just chosen ethene for the simplicity of things. And here, what's happened is that it's reacted with the permanganate, right? And it's produced this ethyl, this 1,2-diol, right? So that means it has two hydroxyl groups as well as this dioxide. So that's the specific chemistry that's going on. So I just want to separate the observation from the actual chemistry. The observation is what we see. The chemistry is what causes that observation to occur. So this is what's causing the observation to occur. It producing this brown precipitate is the observation itself. Yeah. So I just want to make that distinction. So here, right? I'll get you guys to put your answers in the chat. Which one of the following rows correctly describes the result of a bromine water test? So here we have pentene, pentane, hexene, hexane. Yeah. So here, which one would you guys say it is? A, B, C, or D? Remember, what are we looking for the bromine water test? So we've got Salam saying A. Go to Meth saying A. Anyone else? Any other answers? Joe, Swayan, Blessing. On your life, it's B. So here, right? Oh, what is happening to me? Do I have something on this? Say why. Yeah. So here, it's not A. Yeah. A wouldn't remain brown. Remember, this is an alkene. Yeah. So the alkene react with the bromine water. Alright. You aren't speak. Okay. The alkene won't react with the bromine. Will react with the bromine water. So it shouldn't remain colorless. Yeah. Here, B. decolorizes from bromine from orange. No, this is an alkane. This won't react, yeah? So we have an unsaturated, we have an unsaturated, and we have a saturated, yeah? C, hexene decolorizes. It's not unsaturated though, yeah? And it won't decolorize because it, oh wait, it will decolorize, but it's, oh wait, my bad. This is hexene. It will decolorize and is also, this shows that it's unsaturated, yeah? Because it's an alkene. So the answer here is actually C. I just want to get an idea from everyone. Emeth, why did you choose A? And I've lost Emeth. I trusted Salam. Okay, so Salam, why did you choose A? I just want to hear. I'm not like ratting you out. It's just like I want to get an idea.
Because it said results of a bromine water test. So this doesn't it go from an alkene goes from unsaturated to saturated because there's all single bonds.
So no, it's not that it goes. We don't care about what it goes from, right? The bromine water test tells us is if the original compound was saturated or unsaturated, not the product. Yeah, because the product is always going to be saturated. It's about the original thing that we had. So here, and plus pentene won't remain, it won't remain brown. It will react with that bromine water because of that organic pathway. Does that make sense? Does that clear that up? Okay. So I'll keep moving forward. So here, the manganese ion changes. The manganese ion changes oxidation states and is responsible for the color change. How does the oxidation state of manganese change from KMnO4 is converted into MnO2 in the presence of an unsaturated compound? So what happens to the manganese? Anyone have any ideas? A, B, C, or D? This is a little bit of the redox chemistry. Joe says A. I should really start hosting these on Zoom so I can put up like a poll or something. Because co-host. So Emeth didn't copy it, but yeah. So here the answer is A, yeah? The oxidation state of this one, so oxidation state of oxygen is -2, oxidation state of potassium is +1, so the oxidation state of the manganese must be +7 to balance them out. And here, this one goes from -2, this one has to be +4 to balance out, so it's reduced, right? Also, the other thing is you could take out answer option B and D, because remember, manganese permanganate is a reducing agent. So, I mean an oxidizing agent, which means it's reduced. So, now we moved on to the acidified potassium dichromate test, right? So here, this if we essentially, what's it saying is, why is this pen like it's on the float mode for some reason? That's weird. Let me see if I can fix that really quickly. It shouldn't be on this float mode. I should be able to press it down. But I'll keep explaining this one, right? Essentially what's happening here is that with the acidified dichromate, it uses that oxidation pathway. So does everyone remember that the oxidation pathway from the oxidation pathway? So the oxidation pathway is that a primary, secondary, or tertiary, a primary and secondary alcohol will be oxidized. A primary alcohol will be oxidized into a aldehyde, yeah. So aldehyde, and then if we oxidize it further into a carboxylic acid, yeah. Sometimes what they'll do is that they'll completely skip the aldehyde and go straight to here, yeah. And that's the oxidation of primary alcohol. With a secondary, right, what's happening there is that the secondary goes to a ketone and can't be oxidized further. and then tertiaries don't oxidize at all. So what this allows us to do, essentially, is that what this allows us to do is it tells us if we have a primary or secondary alcohol present. So essentially, what we do is we react the alcohol with we react the sample with a sample of acidified. It needs to be acidified, right? Acidified. So you literally say H plus Cr2O7 2 minus, yeah? That's acidified dichromate, yeah? And what should happen is that you should either, if it's a primary alcohol, you should get a ketone. If it's a secondary if it's a primary alcohol, you should get an aldehyde. If it's a secondary alcohol, you should get a ketone out of it, yeah? And this is just pulling from the organic pathway stuff that we did yesterday, yeah? This isn't new stuff. This is more or less just reinforcing the stuff that you've learned before. Does anyone have any questions about that at all? So, but the only thing is we can't actually determine if it's a secondary or primary because both of them get oxidized, yeah? All we can really determine is that we don't have a tertiary, and we also have a, thanks bro, thanks for that. PC's cool, it's old as shit, but it's cool. So does anyone have any questions about that? Give me a thumbs up if that makes sense. Thumbs up all around. If you have any questions, you can always shout out. He plays Overwatch. Yeah, dude, I don't play Overwatch, bro. I swear. On God. On God, I don't play Overwatch. So, here we have the Lucas test, yeah? Now, the Lucas test works for all alcohols, yeah? So the Lucas test is a specific type of test. Essentially, if you react any alcohol with a with hydrochloric acid, you should expect it in the presence of a zinc catalyst, you should expect it to get cloudy, yeah? So here, the observation is it gets cloudy. This is the underlying chemistry which causes it to get cloudy here, yeah? So this is able to just determine if we have an alcohol present, yeah? It's less specific than our dichromate test because we don't know if it's a primary, secondary, or tertiary. But it allows us to determine, is it an alcohol? And then from there, we can do some other tests to figure out if it's a primary, a secondary, or a tertiary alcohol. So does that make sense for everyone? Is that all good? Emeth, blessing, is that all good for the two of you? Just making sure. Not too sure. What do you mean, Emeth? What are you not too sure about? You can unmute yourself and say if typing's a bit of a pain.
Like the test that you use to like determine which one's a primary and secondary.
Oh, so this one here, remember the oxidation pathway that we talked about yesterday? This one's just the oxidation pathway. So we have the oxidation of a primary becomes an aldehyde and then a carboxylic acid, yeah?
Yep.
And then we're just using that, we're just using the fact that we know that organic pathway to determine we can't determine if it's a primary or secondary. We just know that there is a primary or secondary alcohol there. Does that make sense?
Yeah, I think so.
So we just see it react. We technically, what we observe is technically just the color change. Yeah. So we observe the color change from orange to green, and that tells us it's reacted, which means that we either have a primary or secondary alcohol there. We don't know if which one it is. We just know that one of those things is present. Yeah. And here the observation is that it turns from orange to green. Yeah. I should probably make sure I talk about the observation because in an exam question they'll tell you to talk about the observation. Same thing with the Lucas test. The observation, it turns from colorless to cloudy, right? And this is the underlying chemistry that's going on. So we just add hydrochloric acid here, yeah, in the presence of this catalyst, and we get like these things out. Now, I don't think you really need to know the Lucas test because different textbooks focus on different tests, yeah? But you can use all of these tests when you're talking about in your exam. The examiners will give marks for correct chemistry. So I'll keep moving on from here. So we have Tollens test, yeah? Tollens test is specifically to determine if we have a primary or a secondary alcohol. So the first thing that we do in tolerance test is we do the acidified dichromate test, yeah? And that determines if there is a, that there will determine if we have a primary or secondary alcohol. So that's just the acidified test, yeah? However, we follow it up by the silver mirrors test. Essentially what we do is if we react the aldehyde with silver, or here this is going to be silver plus NH3, or silver ammonium silver, yeah, or silver ammonium, I'm not exactly sure what the name is, yeah, so silver ammonium ions, right? If there's an aldehyde present there, what's going to happen is it undergoes this reaction, yeah? We'll undergo this oxidation, and we'll see here, right, that we'll have almost this silver mirror like substance forming. Essentially, silver is being formed here. That's what it means when it says the silver like substance, yeah? So here, this only works if an aldehyde is present. If a ketone is present, this won't work, yeah? So here, if we see a silver mirror like substance, yeah, after doing this test, it's the original sample that we had was a primary alcohol, yeah? If we don't see that silver mirror, yeah, it's going to be a secondary alcohol, yeah? If it doesn't react with the acidified dichromate, it's just a tertiary alcohol. So does that make sense for everyone? Just trying to join. Hello, who is this? If you don't unmute yourself and say what your name is, I'm gonna kick you from the call.
Kana Mishra.
Okay. Are you here for the chemistry class?
Yeah.
Okay. You can stay. Don't do anything because I had people come in here yesterday and do some stuff, and I had to take down the recording for it.
Okay.
All good. So I'll just mute you there. So perfect. So does that silver mirrors test make sense to everyone? It will have the recording if you guys need to look back on any of this stuff at all. So here, to qualitatively determine the presence of a primary alcohol, which type of chemical test is commonly carried out? I'll ask Joe, what do you think the test here is that would be going on here? So how can we determine it's a primary alcohol specifically? Is your mic working? Oh, okay. I'll do it then. So here, if we have a primary alcohol occurring, yeah, the qualitative test that we'd first do, or to determine if there's a primary alcohol, the first thing that we do is we see if it reacts with acidified dichromate. So we see if it reacts with the acidified dichromate, yeah? If it reacts with the acidified dichromate, we know we have a secondary or primary. Then afterwards, what we do is we do the silver mirrors test, right? We do the silver mirrors test. Or we react it with the AgNH3 squared plus solution rates. Yeah, okay. The NAG3 squared plus solution. And if there's a reaction there, right, if we see a silver-like substance form, that means here we know we have a primary alcohol. Yeah? So essentially what I'm doing here is I'm naming the test and I'm stating the observation. Yeah? That's the big thing that you want to do. You like name the test and describe the chemical properties of the test and then explain the observation. So here I would observe a color change from orange to green. You don't need to remember the specific color change. It's in your data book. Yeah? Then for the silver mirrors test, right? I state the silver mirrors test and state, well, I'm going to react it with the AgNH3 plus, right? NH3 2 plus. And then afterwards, what I should see is a silver-like substance form. And if I see that silver-like substance, it tells me that there's a primary alcohol present. Does that make sense? Thumbs up. What's up, Salon?
Why don't you do the Lucas before the silver? Because can't you do that?
So the Lucas test only tells up if an alcohol is present. Yeah.
Oh, okay.
So
Yeah.
that the Lucas test, the Lucas test, would be useful for just ask, oh, how can we determine if an alcohol is present? So here, wait, I don't think. Actually, I want to see if you guys can do this. What type of reaction occurs during the formation of the silver mirrors? So here we have displacement, combustion, neutralization, and redox. What do you think it is? A, B, C, or D? Type it into the chat. What do you guys think it is? A, B, C, or D? So Emeth says C. D. Anything else? Anyone else want to guess? Blessing, Swayham. Is it Kahan or? So I'm definitely mispronouncing your name. Here it's D, yeah? Because what we see is that we have here, this is being turned into Ag. We see a change in oxidation state. I'll introduce myself. My name's Kahan. I'm from India. I'm studying year 12. My worst subject is chemistry, but IDK, but I can't understand chemistry well. Okay. That's all good. That's all good. That's why half these guys are here. It's to get better at chemistry. So essentially, we see that there's a change in oxidation state. And I'm just going to say this now. We haven't really talked about either of these two reactions, and it's definitely not a combustion. Yeah? So, keep moving on. Which one of the following types of alcohols does not readily react? Primary, secondary, tertiary, or all of the above? Sorry if I disturbed the class. No, it's all good. It's all good, man. Don't worry about it. So what do you guys think? A, B, C, or D? Right? Which one of these does not readily react? We have C's, we have a C. We have another C. We have another C, C. So, the answer option here is C. Does that make sense? It's because the tertiary alcohol literally just doesn't react. Yeah? Now, we have our acid-base test. Yeah? Essentially, so this one okay. There's a variety of ways we can perform this one. Essentially, to determine if a carboxylic acid is present, what we can do is literally dip a piece of litmus paper in, and if it becomes red, right, that means there's a carboxylic acid present, because that means there's a low pH, right? The more red or the more darker red a piece of litmus paper becomes, the more the high concentration of acid there is. And the only organic molecule that we know of which produces this is going to be a carboxylic acid. Yeah? There's no other acidic homologous series. So does that make sense for everyone? This is like a pretty straightforward one. You just dip a piece of litmus paper in, see if it turns red, right? And that tells you if a carboxylic acid is present. So it makes sense. Sorry, Ham. Anyone else? Everyone else? Wait. Do they give the litmus paper color? Wait. No, they don't give the litmus paper color thing in the data book. But another thing that they do have in the data book is the phenolphthalein. Yeah. Essentially, what we should do, we should see a color change. If we have if we put phenolphthalein solution in, so we should see the phenolphthalein become, I think it's pink, yeah? If you look in the data book, I don't remember the exact one. Wait, give me a second. My bad. So yeah, if you want to use the phenolphthalein indicator, right? That one's in the data book. You should see that it should become pink at low concentrations. Yeah, it's either pink or colorless. I don't remember which one it is. I'm pretty sure it's pink. So does that make sense for everyone? Yeah, pink dilute. Yeah, I see. Now this is another carboxylic acid test. Yeah. So here, this carboxylic acid test is instead reacting. So if we act it with a metal carbonate or a metal bicarbonate, right? We should see that here yeah, we see this formation of this sodium ethanoate. Yeah, this wait no. Therefore, the sodium unknown example. Oh yeah, that's what I mean. We should see the presence of some gas being formed here. That's what I mean. So here, right, if we have a carboxylic acid, we react it with a bicarbonate, we should see some sort of carbon dioxide being produced from this reaction, yeah? And that indicates here that we have a carboxylic acid presence. So far we've covered the presence of a saturated or unsaturated compound, the presence of an alcohol and which type of alcohol it is, and now we've determined the presence of a carboxylic acid. Those are the main three that they'll focus on, yeah? Because everything else is really hard to test. So I'll keep moving on from here, right? We also have esterification. Here for esterification, if we think we have a carboxylic acid present, what we can do is that we can react that carboxylic acid with an alcohol, or if we know we have an alcohol present, we can react that thing with a carboxylic acid. And if we remember, if we react it with the strong sulfuric acid, yeah, we should have a condensation esterification occur, yeah? So a condensation reaction occurs, and it produces this ester, yeah? And then afterwards, what happens if we, like, to tell if an ester has been formed, what we can do is we can smell, we can smell the solution. And if we remember all the way back to our organic chemistry, when I pointed out that they had a pear shape and a pineapple shape over the esters, it's because the scent should be a pear scent. The scent should be either a pineapple scent. We should be able to smell this like sweet scent, yeah. So like basically the background is that most of the sweet like synthetic products that we see are made of esters, yeah. So you should get this sweet. It says here the sweet aromatic scent of an ester, right? Implies the presence of a carboxyl group. So we can do this for an alcohol or carboxylic acid, yeah? We just have to add the other and then add concentrated sulfuric acid as the catalyst. And then afterwards we smell it and we see what we get. So does that make sense to everyone? Any questions about that? All good? Thumbs up, thumbs down, thumbs to the side. Now, right now, we haven't actually, like, here, all we're doing in most of these tests is determining the presence of, like, a functional group, or we're determining the presence of something. We're not actually determining what the compound is. So that's the key thing here. We're not determining what the compound is. We're just like giving ourselves an idea of what the compound could be. So here, it could be alcohol, it could be so on and so forth. So here, carboxylic groups are the functional group found in mineral acids, carboxylic acid, diprotic acid, inorganic acids. Which one do you guys think? This one should be straightforward, yeah. I'd kind of crash out if anyone picked anything else. I'd be like, what the fuck, guys? What the fuck? Anyone else? Joe, Blessing, Emeth? Do we also think it's B? Yeah, B. B. I'm gonna say D. I want to crack. Oh no, I can't. No, now that I know you've done it on purpose. I don't know what's up with my pen today. I think it's because it's on hover mode. It shouldn't. I think it's like sees me moving around. Anyway, carboxyl groups are made up of carbonic and carbonyl functional groups, ester and hydroxyl functional groups, hydroxyl groups and carboxyl functional groups, ether and ester functional groups. So what are they made up of? A, B, C, or D? So here we have. I'm very sorry that like it would do that. We'll do these lines. I'll have to fix it a bit. Which one of the following is not a possible qualitative test that could be used to identify an organic molecule? So is it pH paper, acid base indicator, aromatic aroma, soil emitters? I don't know why everyone here is saying C. The answer is D. This one's D, because it's asking for organic acid. These are all tests for acids. Yeah, sure you did, man. Sure you did, man. I love this guy, man. I understand it. Wait, let me. Sorry about that disturbance. So those are the chemical tests that we need to know. Yeah, and it's more or less most of these things you can probably just like I'll say this now. I've seen a bunch of trial papers and I've seen a bunch of the exam which focuses on those sorts of tests. Yeah, because it's like chemistry is trying to get more into the application based side of chemistry. So if you can just remember those tests, or if you can just remember the basic pathways, right, you'll be able to do those tests very quickly. Like those will be just quick marks for you on the exam. You'll be able to finish like, you know, a decent chunk, like one whole question, which is about like 8 marks in about like a couple minutes, like 2 to 3 minutes, if you know those tests really well. Because you don't have to write in full sentences. You just have to be able to write in dot points. I was gonna say qualitative and quantitative, but you know, bro. Like I felt like the aromatic thing was fishy. Okay. The big thing there is that those are qualitative tests, yeah? So here, qualitative tests, I'll ask Swayam, what's the difference between a qualitative test and a quantitative test?
One had like one test numbers, one test how it looks.
Yeah,
Is
yeah.
that what it is?
Yeah, so one test is based on observation, one test is based on how it looks. So I'll keep going forward. So, yeah, before I start going on to about this. So, I'm hoping you guys know what the boiling point and what the melting point is, because this whole section's about boiling point and melting point. Yeah? We'll be discussing the process of fractional and simple distillation. Who is trying to join? So we'll be discussing the process of fractional and simple distillation. Yeah? And these we'll be dealing with like how both of these tests work and why we do them. Also, this is what volatility is. They just might like I would say it's like something people don't know anymore. That volatility used to be a bigger thing in the old study design. Now it's not. So we'll make sure like I would recommend just having on a cue card, because then it's like well, like you won't forget it then, and then like you can like keep remembering it, because like I guarantee you that one like it'll be some like 1 marker question on the exam. It'll be like, oh yeah, what is volatility? Christy. So we'll go into the melting point test. Now, the idea of the melting point test is to focus on purity. It's determining purity. That's the whole goal of the melting point test. Yeah? So here, right, melting point test simply focuses on converting from solid to liquid. Yeah? A pure compound should have a very defined melting point. Yeah? So here we know water's melting point is 100 degrees. Yeah? It's very defined. It's not 99, it's not 101, it's 100 degrees exactly, yeah? So if we had pure water and we heated it up to 100 degrees, we'd expect it, wrong idea, I'll use ice, yeah? If we have ice, yeah, and we know ice melts at 0 degrees, yeah? If we get the ice to 0 degrees, we should expect it to melt, yeah? So that's the melting point test. It's very defined, the pure substance. and there's only going to be a small range in which that might vary. Like, you know, it might start melting at -1 degrees, or maybe at 1 degree. Yeah, very small range. An impure substance will have a lower melting point and a broader range of melting points. So, for example, water, right, ice, which may regularly melt at 0 degrees, might, if it's impure, let's just say it has a bunch of, you know, like dirt in it, yeah, that will cause it to, that will cause its melting point to decrease, that will cause its melting point to decrease maybe to -5, right? It might start melting at -7. And it will also be a lot broader. So it might have its melting point, it might start melting at -7, yeah? But it could also start melting at -2, yeah? Basically, if I grab different sets and samples of it, I should expect a variety of melting points with a very broad range of melting points. Does that idea make sense to everyone? Is there any questions about that one? So basically, a pure substance is well-defined melting point, yeah? An impure substance has a, like, if we take different samples of it, right, we should get different melting points that are lower, as well as the idea that each sample, we'd expect to have a different set of melting points. Like, if I grab 2 sets of pure water, I should expect them to melt at 0. But if I grab 2 sets of impure water, I should expect, like, maybe one to be at, like, -5, maybe one's at -3, you know, maybe another one's at, like, -10. Yeah? That's what impurities do to melting point. Does that make sense? The rest of this slide is mostly yap. I'll be honest. Like, the rest of this one's just purely yap. Essentially, just describes how, like, oh yeah, the lattice is irregular, which causes the melting point to change. Yeah. They don't want you to go that deep into it because they're not dealing with we're not dealing with like specifically metals. Yeah. So, and well, like, the idea is that if there's impurities, it makes an irregular lattice, and an irregular lattice requires less energy to overcome. Yeah, that's all. That's the only idea that the rest of this slide tries to show off. So, this is what the melting point test looks like. I'm just gonna say this now. This is the most simple, straightforward test. You look at it, and you see when it melts, and you write that down. That's all you do, yeah? They give you this whole apparatus, but all you're doing is you're looking at it, you see when it melts, and then you compare that to, like, what a pure substance is, yeah? So let's just say we have a pure substance that melts at, like, let's just say 24 degrees Celsius, yeah? And here, this sample here, it melts at, like, 25 degrees Celsius. We can say that's a relatively pure compound, yeah? But let's just say our pure substance melts at 24 degrees Celsius. And this one over here melts at, let's just say, like, 17 degrees Celsius, yeah? We consider that impure, right? There's a big difference in those ones. So does that make sense? You literally look at it, and you see if it melts. And if it's lower, go on, Salon.
If it's impure, does it always have a lower melting point?
For the sake of VCE chemistry, yes.
Okay.
There's no special cases in here. Different substances or the same substance but impure. It's the same substance but impure, yeah? So it's not different substances. It's the same substance but impure. Okay. So I'll keep moving on. Like, this test, it's all it is it helps you determine the purity of a substance. That's the goal of this test, is to determine the purity of a substance. And we determine the purity by using the melting point. So, this is basically just like a summary of the slide, right? If the melting point is lower and broader than that of the pure substance, then the substance is not pure, it is a mixture, right? And if the melting point is lower, yet well-defined, then the unknown substance is likely a mixture of pure compounds, yeah? So, this last stop point here, right? Just be mindful of it. Most likely it won't really come up. You can think of a substance which is a mixture but pure as, like, something like bronze, yeah? Bronze is made out of like some percentage of like one metal and then some percentage of another metal, yeah? So you'd expect bronze to it's a mixture, but it's a pure mixture in the sense of it only has those two metals, yeah? But like if it's a mixture that's impure, right? Or like it's a mixture of impure compounds, right? You can imagine just like there's 1,000 different things in there. That could be there. It could be like water. It could be like, they could have ions in it. It could have a bunch of stuff in there. So does that make sense? Does anyone have any questions about that at all? If you do, put your hand up or give me a thumbs up if we're all good. Okay, chill. So melting is best described as a chemical change, physical change, chemical reaction, breaking of bonds. D. What else? What do you guys think? D. Does anyone want to go against the status quo? B. Okay. Does anyone think it's C or maybe A? What do you think, Cav? What do you think, Swayhan? What do you think, Swayhan? What do you think, Blessing? A. So, the answer here is B. Melting and boiling are both physical changes, yeah? A chemical change requires a chemical reaction. If no who are you feeling like, bro? Dude. A chemical change requires a chemical reaction to occur. That's just like that's like baseline thing, yeah? So here, chemical change and chemical reaction could basically be the same thing. And breaking of bonds, yeah? This isn't breaking the bonds, right? When we say breaking bonds, we're talking about they're talking about the intramolecular bonds, yeah? We're not talking about the intermolecular bonds, right? So here, this isn't what we mean. We're talking about a physical change. We describe it as a physical change. Essentially, actually, sorry. We could describe this as breaking of bonds, yeah? But the best description of it is as a physical change, yeah? So this is more or less the idea of the best description, yeah? Anyone have any questions about that at all? If you don't, put your thumbs up, thumbs down, and then have a go at this one. So the melting point test, so you have to understand it. So here, melting point determination can be used to assess. So we have this swaying says D. What does everyone else say? D, D, D. We got D's all around. Do. E or B. But you can't pick two. It's a multi. It's D. If it's something not in the lesson, I'll slime you. No, it's D. It's D. So here, right? The melting point test. We haven't talked about any sort of functional groups here. This is a purely physical change based test. Yeah. Right. It's not talking about the structure of the sample. We can't determine the structure of the sample. And here it's not talking about the density of the sample. Right. We've never even spoken about that. It's purely about the purity. What effects do impurities have on the melting point of a compound? Increase, decrease, or decrease, no change. So we have BBs. We have anyone else saying B? Anyone else? Anyone else? Oh, the answer's D. No, I'm kidding. The answer's B. So here, the answer option is B. So now, here we have our two types of distillation, right? This one is simple distillation. This one over here is fractional distillation. Now, I'll explain what simple distillation is first. Simple distillation allows you to separate two compounds based on their boiling point. Yeah? So, let's go back to fuels chemistry. Yeah? Remember when we produced bioethanol? Yeah? We had the bioethanol in an aqueous solution. And we talked about this idea of distilling that. Yeah? So here in this compound, what you might have, you'd have water and you'd have ethanol, yeah? And you'd be able to separate them based on their melting point. Ethanol has a hot, wait, where's my mouth? Ethanol has a lower melting point, about 78 degrees. You don't need to know that, right? But it has a lower melting point than water. So here, the idea is that the ethanol will boil out, yeah? It will become a gas. It will boil out, it will go up, and it will go through this tube, and it will be collected over here, yeah? Whereas the water would stay here, because the water's melting point is 100 degrees. So here, it allows us to separate two compounds from one another, yeah? That's the whole point of distillation. And simple distillation is only for two compounds, yeah? Only for two compounds, yeah? So here, if we have the ethanol and we have water, and we're trying to separate the two of those compounds from one another, we can separate them in this way, yeah? Now, another thing about simple distillation is that it can't really differentiate between things that have really close melting points. For example, if ethanol, let's just say, had a temperature of 98 degrees, and water has a boiling point of 100 degrees, then, right, it would be hot. Like, we wouldn't use simple distillation here, because simple distillation works to separate two compounds of very different melting points or boiling points. Whereas for fractional distillation, right? Fractional distillation is a little bit more precise. It can be used for multiple compounds, right? And here, what it does is that it essentially, like, it essentially just fractions them all off, yeah? So here, this part of the column could be, let's just say, 100 degrees. This part of the column could be, let's just say like 98 degrees. This part of the column is going to be like 70 degrees, yeah? And so on and so forth. So they're different temperatures. Each part of the column are different temperatures, yeah? So here, let's just say we have multiple compounds in here, and they all have very close melting points. Let's just say we have like, we have our ethanol in here, as well as, let's just say, our let's just use ethanol, yeah? So this is ethanol. So we have ethanol and ethanol. Ethanol has this melting point. Ethanol might have this boiling point. Ethanol might have this boiling point, yeah? So here, what it like allows us to do is that we can have multiple compounds in here, and we can separate multiple compounds so that we get the one that we want. So here, right, we only get the ethanol out, because at this point, what's going to happen to ethanol is it's going to condensate, right, going to turn back into a liquid and fall back into the solution. Whereas the ethanol, it stays as a gas and then passes through this thing. Does that make sense? Anyone have any questions about that? So essentially, distillation is a separation technique, which separates things based on the boiling point. Simple distillation is for two compounds that have very different melting points. Fractional distillation is for multiple compounds with very similar melting points. Yeah? Thumbs up, thumbs down, thumbs to the side, thumbs all around. Okay. So here, boiling point is best described as a chemical change, physical change, chemical reaction, breaking of bonds. What do you guys think? We have here, we have D. It's a D. What do the rest of you say? We have Meth saying D. Who agrees with the Meth and Salam? We have Swayham saying B. He's breaking the mold. We have a couple people saying B. Here the answer is B. Yep. Again, it's not a chemical change, it's not a chemical reaction, right? Because there's no chemical reaction going on here. And here, right, we never talk about breaking covalent bonds, right? We never talk about breaking. Salam, you're not just rage baiting me, Math, aren't you? You're intentionally getting them wrong to see if Imheth follows. But we don't talk about breaking covalent bonds. We talk about breaking our hydrogen bonds, our intermolecular bonds, but not our covalent bonds. I was just spectating. But he had two options in front of him. Boiling point determination using fractional distillation can be used to identify the relative reactivity of a sample, identify the functional group, calculate the density, verify the components of a compound. What do you guys think? A, B, C, or D? This one might be a little bit harder. But if you guys think back to fuels chemistry, you might be able to abstract the answer. But I got two people saying D. D. What does Kavinu emit? Oh wait, emet's what it is. Kavinu. What do you say? D. What about you, Blessing? What do you say? Just trying to be different. Bro, you guys actually gonna like? I'm gonna like. I'll get you guys all together at the end of the year to have like. Can't even answer nowadays. Now Emeth changing his answer because he thinks he's tricky. No. The answer is D. So here, again, it's a physical change, right? It won't involve anything to do with the functional. Oh, well, it'll have a little bit to do with the functional groups, but it won't help us identify what functional group is there. We haven't spoken about reactivity at all, and we haven't spoken about density. Here, it verifies the components of the compound, because think about it. If I can separate the compound, I can figure out, well, what's there, yeah? Like, if I can separate, let's just say I separate the ethanol from the water, I can realize that, well, this mixture was made of ethanol and water, like, yeah? And like, if you think back to fuels chemistry again, when we talked about fractional distillation in the context of fossil fuels, right? It helped us to it showed us the components of our sample. So here, crude oil was made up of, it was made up of natural gas. It was made up of coal steam gas. It was made up of the petrol was made up of the kerosene, bitumen, all this different stuff. Yeah. So here, let's. I swear I had a slide in. Is it? No. Before we go on, boiling point has the reverse effect as melting point. As a substance becomes less pure, right? The boiling point actually increases. Yeah. So as a substance becomes less pure, the melting point actually increases. Yeah. So that's where this question's kind of a scam. I was meant to explain that before. I thought I had a slide on it. That's why I didn't do it till now. But have a go at this question. Is it A, B, C, or D? So A. Yeah, basically given the answer away. So I want you guys to remember that though. For the melting point, it decreases as it becomes impure. If it's impure, if we have an impure compound and we're boiling point, the temperature actually increases. Joe, what are you doing, man? So I did kind of give away that answer. That's my fault. I thought I had another slide between it. That's so tough. Oh yeah, but impurities still create that broad range of melting points. Yeah, it still creates that broad range of melting points. I want you guys to remember. So wait, so like impure substances and impurities are different things. No, impure substances and impurities are the same. So what causes impure substance is impurities. They are, so then why did it increase? Oh, why did it increase? That's a great question. So here, right, when we're overcoming, so a liquid converting into a gas, right? Here, why it increases is because this irregular lattice in a this irregular lattice, it like for a solid, it has to be a rigid lattice. So having irregularities in it means that it's easier to overcome those bonds. Yeah, so that's why the melting point works like it does. But the boiling point, we have a liquid. The liquids are all moving around. Yeah, so they're already moving around. And when we have impurities in them, right, the irregularities are they almost create they almost place put places where the liquid becomes less of a liquid. It becomes more of a solid. Yeah. So essentially, it like pulls everything towards it. Yeah. And to overcome that, you need a lot more energy. Does that make sense? But the main you won't really need to explain this one. Yeah. I'll see if I can find a better. I'll see if I can find a better explanation for this for you. But here, the idea is that impurities for boiling point increases the boiling point. It has different effects. So now we've gotten to everyone's favorite. Can you put your thumbs up if you've done a titration before? Just like gives me an idea of who has and who hasn't. Blessing, have you done a titration before? Okay. So, too many times, too many times. So I won't have to explain too much of this stuff. We pipette our aliquot, yeah? So our aliquot is generally the thing that we're analyzing, yeah? And we pipette that, and whatever we pipette is called our analyte, yeah? So everything in here everything that we pipette out is our analyte, is what we're analyzing, yeah? We have our burette, and our burette slowly dripped in, and then we have a color change, yeah? So you guys have probably seen this about 100 times. Like, I guarantee you. Now, the big thing that you want to realize is that the analyte can actually be in both the burette and the pipette. I mean, in the conical flask. It doesn't really matter. Because all that matters is that we realize that we're able to do that stoichiometric change, yeah? So it doesn't actually matter if we have the thing that we're analyzing, the burette or the pipette. We should have the same result coming out. We generally put it in the conical flask because the known moles one we probably have a large quantity of the one that we know the moles of compared to the ones that we don't know the moles of. Yeah. So that's why we put that one in the conical flask, just in case we might have to use a lot. So does anyone have any questions about titration? Now, the big thing that you guys just need to remember is that we have two types of titration now. We have our redox titration and we have our acid-base titration. So we have those two different types of titration, yeah? Our acid-base titration focuses on the neutralization. But the redox titration, which is what Year 12 chemistry focuses on, uses a redox reaction. And they're very specific. Acid-base titrations can happen for any acid and any base. But redox titrations, you have to have a specific reagent to react with this, yeah? And we'll talk about that a little bit more. So sometimes you might need an indicator, sometimes you might not, yeah? So the presence of an indicator could be necessary. For example, we might need it in, let's just say, a reagent that is colorless, right? Or a redox reaction which is colorless. But sometimes we just won't need it at all. So for example, with our dichromate example, that's technically a redox reaction. That could be a type of redox titration there. Yeah. We see that the color change will go from orange to green. Yeah. So the titration process is exactly the same. Remember, you need concordant titers, and you need to measure at the bottom of the meniscus. You guys remember this? Is anyone unfamiliar with this at all? Is that all good? Thumbs up, thumbs down, thumbs to the side, thumbs all around. Yeah, Emat is good. Salam. Swayam. What about Kavinu and Blessing? What do you guys? Okay. Perfect. So, oh yeah, I'm hoping you guys understand that these three are concordant titers. They're concordant because they are the greatest distance is 0.1 apart from each other. Yeah, so here this one is 0.5 apart, this one's 0.5 apart, so they're concordant. Yeah, and we use those concordant titers, right? We average them out to find out what our approximate, like what our average titer would be for this. So here it'd just be 19 plus 19.05 plus 19.1, which is just going to be 19.05 if we divide those three values by 3. So that's nothing too crazy. What do you mean PMO? Joe, what do you mean by PMO? I don't know what PMO means. Am I getting old? He's too piss me off. I'm not that unk, bro, I swear. Now this is the big thing that most people that most people forget. It's how can making a mistake stuff up your calculations and can stuff up your final results. So here it says effects on accuracy of calculating concentration if unknown is in the conical flask or the burette. If we rinse the burette with water, we overestimate the conical flask and underestimate it if the unknown compound is in the conical flask and the burette respectively. And that's because the solution in the burette becomes more dilute. Yeah. So essentially what's happening here is that when we rinse it, when we rinse the burette with water, right? What we want to rinse the burette with is whatever we're putting in the burette. Yeah. The reason being is because if we rinse it with water, right, there could be water droplets left over, and those water droplets that are left over could lead. It will lead to there being some like leftover water droplets. And if you guys remember, N equals CV, right? If we then put in what we're putting in the burette, yeah, what's going to happen there is that the water droplets inside will increase the volume and it will decrease the concentration. Yeah. So it will decrease the concentration of whatever we're putting inside. So we think it's like 0.1 moles, but really it's 0.99. Yeah. Or 0.099. Yeah. I lost 3 marks in a sack last year because I of this was I was fuming. Yeah, no, I can imagine. A lot of people forget about this. Just remember the table. So big thing is you rinse the burette with whatever you're putting in the burette. You rinse the pipette with whatever you're putting in the pipette. Yeah, and here are the effects that it has if for the unknown concentration, and this is the reason why. Yeah. For the conical flask, you rinse the conical flask with water. Yeah. And the volumetric flask, you also we generally use a volumetric flask as well. You also have to rinse that with water. Yeah. And then if you miss the indicator, you overestimate, underestimate, big discrepancy between the endpoint and the equivalence point. So remember, we want the end point of a titration to be as close as the equivalence point. The equivalence point is the stoichiometric equilibrium. So when the number of moles of one is the same as the number of moles that we put in to the conical flask, like balances out with the number of moles that we've dripped in. Yeah. So it creates like this sort of curve. That's the equivalence point. Here's the end point when we start to see that color change. We want them to be as close together as possible. Does anyone have any questions about this? Is that all good? Thumbs up, thumbs down, thumbs to the side, thumbs all around. What do you guys think? During titration, a burette is used to deliver a solution into a. What is happening? Is it A, B, C, or D? So if two people say B, anyone else have B? B. Okay. So here the answer option is just B. So the answer option here is just B. Yeah. If anyone gets this wrong, I don't know if I should be disappointed or not. But what is the units of a C in the equation N equals CV? Yeah, so we have D all around. Yeah, the answer option is D. I'm not even gonna circle that. Yeah, okay. Have a go at this one. This is in your data book. So if you consult your best friend, you should be fine. The hell is it? The hell is a. Yeah, the answer is C, because it's N equals CV, which means that V equals N over C. And then here, which one of the following options contains three concordant types? So nothing here is really new to you guys. It's more or less, do you remember the titration that you've done probably 100 times? Depending on what school you go to. I remember at my school, we did like a titration every year. I think I did a titration for year 12 as well. I did read off titration for that one. So we have one person saying C. C, C. Yep, C is the correct answer, guys. I can't read numbers. But does it make sense? Because we have these three titers here, which is 0.1 milliliters apart from each other. So that's why they're concordant. Now here, yeah? I'll get you guys to have a go at this calculation. How many moles of chromium 6 plus are present in 200 mils of 0.25 moles per liter of Cr2O7 2 minus? What do you guys get for this? Type your answers into the chat. Or if someone wants to call it out, they can. This is just me checking if you guys remember. 0.05 moles, yep. Everyone else agree with that? Yeah, 0.05, 0.05, yeah, 0.05, perfect. Okay. Have a go at this one, guys. Crazy difficult calculations today. Again, there's nothing really new in this redox titration one. I almost got milliliters to liters on, but so here, what is the volume in milliliters? Let me actually grab my calculator for this because I don't have my trusty. Let me grab my trusty calc. 267 mils. Does everyone agree with that? What is it? What is this? No, no. Does no one else have an answer option here? Oh, you just am I just gonna get aired out? Because here it's gonna be 667 milliliters, right? Because it's gonna be 0.5 divided by 0.75 equals V, which means V equals 0.666 dot dot dot, which means we get here 667 milliliters, because this one here is in liters. So 6, 7. So this is the sort of calculation, like this is one sort of calculation you'll be given here. It says in a self-indicating redox titration. So when it says self-indicating, it means it just doesn't have an indicator with it, right? The one of the reactants has a color change, so we don't need to add an indicator to indicate that color change. An average concordant titer of 24.1 of 0.5 mils. Standardized solution of iron sulfate was used to react with 25 milliliters aliquot, which was taken from a 250 50 milliliter sample of acidified potassium permanganate. The balanced equation for the reaction is this. Determine the concentration of the potassium permanganate solution. So it wants me to determine the concentration of the solution. Yeah. So of the whole solution. So potassium permanganate. So here, right, the first thing that I'm going to do is I'm going to do N of FeSO4 equals 0.02410 times 0.5, right? That's going to get me 0.01205 moles. Yeah. So we found out the number of moles of the known. Now we're going to use our molar ratio. We see that there is a 5-to-1 molar ratio. So we're going to do N of MnO4, right, which is our permanganate, which is what we're trying to find, is going to be 0.01205 times by 1/5, yeah, which is the known over the unknown over known. So here we get calculator, come back. So we get 0.01205 divided by 5. We get here 0.00241 moles. Yeah? After this, then, we can then use our equation, right? C equals N over V, and we can do 0.00241 divided by 0.025 to find out the concentration of our permanganate solution. So here, right, we divide this by 0.025, and we get our final concentration of 0.0964 moles, correct to 2 sig figs, because that's the smallest number of significance here. We get 0.096 moles. Yeah, that's our final answer. Any questions about that? Does that all make sense? Thumbs up if that makes sense. So essentially, I'm finding the number of moles of the unknown. I'm using the stoichiometric ratio to find the number of moles of the unknown. Yeah, and then I'm using the equation N equals CV to find the concentration. N equals CV, rearranging that to find the concentration of the solution. So yeah, these are the steps of the titration, if you guys forgot. I'll just let you guys read over that one. If anyone wants me to explain anything. Is that all good? Thumbs up, thumbs down, thumbs to the side, thumbs all around. So here is this one, right? Limiting reagent calculations. Yeah, I just want to remind you guys how to do limiting reagent calculations. So here we just have to find the moles of both. Yeah. So here the number of moles of the iodine solution is 0.0. I don't know how to do the math in my head. 0.02 times 0.01, which is 0.0002 moles. That's how many moles of iodine solution we have. Yeah. Then we also need to find the number of moles of sodium thoracate, which is going to be 0.02 times 0.005. Here we get a number of moles of 0.00001 moles. Yeah. And here, this is my method to do this. Yeah. This is my method. What I do is that here I look at the ratio that it has here, the stoichiometric number. Yeah. And here iodine has a stoichiometric number of 1. So here I divide this one by 1. This one has a stoichiometric number of 2. So I divide this one by 2. So I get here, right? So here I realize that I get 0.000. Wait, am I putting too many zeros in this? So there's too many zeros in this top one, same with this bottom one. So 0.002, gosh, 0.002 compared to 0.00005, and here, right, I can compare the two. So here, it's going to be sodium thiosulfate as our limiting reagent. Yeah. If I let's just say I wanted to find out how much of the iodine solution was left, I can just take this value away from this one, and then find out, well, here what I have left over is just going to be the 0.00015 moles. Does that make sense? Any questions about that? Thumbs up, thumbs down, thumbs to the side. Whenever I say like, is it all good? So here, when the indicator changes color, this signals that the equivalence point, indicator point, end point, or pH point. So we have C. You guys can, oh, wait, I'll be back in like 2 seconds. Don't copy. Yeah, the C, sure, we believe. See the copy. Yeah, the answer is C here. So we reach the end point, right? The equivalence point is when they're stoichiometrically equal to each other. Yeah. So that just means that should be the point that we finish at, but we actually can't see that, so we use the end point to determine where we finish, which means we technically overestimate all titrations. Yeah. But that's a small price to pay, because it's not like we can just like guess. Well, you know. So here, I just want to show you this curve. You guys have probably seen this for the acid-base stuff, where they have the pH change. Instead, for redox chemistry, what they do is they use this. They use the electrode potential voltage, right, to create the same curve. Yeah. So here it says a redox reaction do not typically involve a change in pH. The equivalence point is instead found by plotting the electrode potential. the electrode potential E against the volume ml. What point of the graph represents the equivalence point? What do you guys think? And just remember, this graph's theory doesn't really change too much from the acid-base one, yeah? We have A, anyone else? A, IDK. So here, this is the end point, yeah? This is the end point. This, whenever it's going vertically up, that's when we reach the equivalence point, yeah? So here the answer is actually B. I know I didn't explicitly tell you guys that, yeah? But, right? This is, again, this is like the stuff from the year 11 crossing over, right? There's a reason I put this question in, is because we didn't cover it. So this is me trying to cover all the bases for us, yeah? And here it says, which one of the following is not commonly used, which is not a commonly used oxidizing agent, as it is too hazardous in schools. Here, like, technically we don't know, right? The textbook doesn't go over this. I was actually reading through this question last night, and I was like, I put it in here. I put it in here because it had this table, right? For some reason, this one didn't, even though this one was clearly referring to this table. But anyway, we don't want to use toxic materials. We're not required to know hazardous materials, yeah, like specific hazardous materials. But the idea is that we don't want to use materials that are too toxic. So, yeah. So, anyone have any questions, comments, concerns? I might get done with this one like earlier than expected. Holy shit! I can't get done with this one like early. Yeah. We got it. Thumbs up, thumbs down, thumbs aside. What do you guys think? So, now I just wanted to bring this up to you, yeah? And because now we're talking about saturation, yeah? So we're talking about the saturation of fats and oils. So we can see here, the more saturated a compound is, the more solid it is. So here, like butter and coconut fat are both solid. For anyone going to Clarendon, for Himeth, Salam, and Kavinu, you'll have Mr. Evans go on a 20-minute rant about how great butter is. Enjoy that because it's great. It's great. But we can see that the more saturated the more percentage of saturated lipids that it contains, or fats, yeah, the more likely it's going to be solid. Does that make sense? Yeah, thanks for the heads up. No problem, bro. Whereas if it contains more unsaturated, yeah, it's going to most likely show up as a liquid or an oil, yeah? The reason this is the case, right, the reason why unsaturated compounds do this is because they have more kinks at the chain, right? So remember those kinks that we were talking about? The kinks essentially cause bends, yeah? So essentially, right, this is what double bonds do. They cause these kinks and these changes in the chain, right? Which means that we can't we can't pack it effectively. Because ultimately, a saturated compound is just going to be like this, yeah? And what the kinks cause, the double bonds cause these kinks, yeah? It's going to look something like this, yeah? It's going to be all over the place. It's not going to pack efficiently, yeah? That's why unsaturated compounds, most of the time, if it's a high concentration of unsaturated compounds, it's going to come out as a liquid. But if there's a high concentration of saturated compounds, it's going to come out as a fat. Remember, unsaturated refers to having those double bonds, and saturated refers to having and saturated refers to just having those carbon-carbon single bonds. Any questions about that? Does that make sense? I don't know if you guys have heard about the kinky chains at all. Don't worry, everyone will laugh at them when we first get to them. But it's chemistry, guys. It's chemistry wording. So whenever actually, I'm not gonna continue that. Anyway. So So this is essentially this helps you, this process here is the process to identify sort of the degree of the saturation of a fat or an oil. So here, right, we can see that there's different degrees of unsaturation. And that's what the goal of this process is. We use an iodine solution to do this. Yeah. Now you don't technically need to really know about the iodine solution. You don't need to know about too much about the iodine solution. You just need to know that here, iodine is what is used to help determine this degree of saturation. Yeah. So we drop the iodine in. Essentially, the more iodine a compound absorbs, the more unsaturated it is. Because again, right, I want you to remember back to that addition reaction, right? Remember the addition reaction between the alkene plus like the halogen, yeah? So here this halogen is going to be iodine. It's going to produce the haloalkane, yeah? I want you guys to remember that. That's the exact same reaction that's going on here. It's having that addition reaction where it's breaking that double bond, and now iodine is joining that chain. Does anyone have any questions about the idea behind this? It's determining the degree of saturation. You don't need to know all of these steps, yeah? I'm just showing them to you here for completeness. The main idea is that you understand that iodine is being used to determine the degree of saturation of these compounds. The more iodine it takes up, the more unsaturated a compound is. Any questions about that? Okay. So here is this new thing for you. This is probably like the only new thing from this whole set. The iodine that my brain gave up 5 minutes ago. Okay, we'll talk about it more in tutoring. We're almost done, by the way. We're almost done. Yeah, we're just doing this iodine calculation. So here, it's the mass of iodine reacted divided by 100 grams of the fat or the oil. So here, a biodiesel consists of a pure substance of this methyl ester, right, with this molar mass. Calculate the iodine value. Now, this is where I need to remember I have my chemistry data book, my best friend. You know, my one and only friend. I don't have any other friends besides the chemistry data book. You don't have any friends besides the chemistry data book. The chemistry data book's always there. Whenever you need a friend, it's the chemistry data book. So if I go down to my section of fats, yeah, I'll see all of my different fatty acids, yeah. These are what my fats and oils are made out of. They're made out of fatty acids. And I see, well, let's look in here. Well, what fatty acid is it? C19H36O2. So which one matches with that? None of them, apparently. So it's none of them, yeah? Here, we need to remember, it says here biodiesel, yeah? So this question's actually tricked us, right? It said biodiesel, which means that we need to find out, well, what original molecule is it made out of? So remember, it has this CHHH bonded with the O, bonded with C, double bond O, and the rest of this chain is just C. Yeah. In the fatty acid version, we don't have this whole thing, right? We just have a H. So we want to take away one carbon, so we get C18 and 2 hydrogens, right? Because we have 1 hydrogen here, so we get H34O2. Now we go back to our data book and we see, well, C18H34 is oleic acid, yeah? And oleic acid has 1 double bond. So let's go back in here. We know we're dealing with oleic acid. So let me just put this pen back on. We're dealing with oleic acid. Now, oleic acid has 1 double bond, which means that only 1 iodine is required to react with it, yeah? So we have 1 double bond and 1 iodine is required to react with it, yeah? So that means there's a 1-to-1 molar ratio here. Any questions about that so far? So 1 double bond means 1 iodine is going to react with it. So now we want to remember the molar mass of iodine. Well, what's the molar mass of iodine? I'm going back into my data book. I'm going to look for iodine. Iodine is over here. It is 126. Yeah, so we have here the molar mass of this one is just 126.9. Yeah, 9 grams per mole. So we have 126.9 grams per mole. That's the molar mass of iodine. We know it's a 1-to-1 ratio. So now what we're going to do, here is we know the molar ratio, we know the molar mass of iodine. Yeah, we're going to assume we have 100 grams of this biodiesel. Yeah, remember the biodiesel. It's just the biodiesel is a biodiesel formed from oleic acid. Yeah, so we're going to use the oleic acid. So from here, yeah, what we do is we find out the number of moles of iodine that we have, the number of moles of the biodiesel we have. So it's going to be 100 divided by 96, and we get here 0.337 ... Yeah, there's a 1-to-1 molar ratio, so this is also the number of moles of iodine that we have. Yeah, remember, for an iodine, there's 2 iodine here. So if we know the molar mass of 1 iodine, we times that by 2. So times that by 2. So here, the molar mass of iodine is 253.6. Then we times this value, 253.6 by 0.337. So times this by 0.337. And we get here 85.743 grams. Yeah? So then, now we can just do 85.73 grams divided by 100, right? 100 grams. And that means here, we just get the value of 0.85, 85. And that is our iodine value. Yeah? That's our final answer. So those calculations were a bit all over the place. So let me summarize. Yeah? First, what we did was we figured out, well, what was the biodiesel formed from? Here it's oleic acid. And oleic acid has 1 carbon-carbon double bond. Yeah? That means we're only going to need 1 iodine to react with it. If it was 2 carbon-carbon double bonds, we'd have 2 iodine. Yeah? Then afterwards, what we do is we take we assume it's 100. Yeah? We do 100 and we find the number of moles of the biodiesel. Then afterwards, we use our molar ratio to find the number of moles of iodine that we reacted. We then times this by the molar mass of iodine. Yeah? So iodine 2, because it only exists as iodine 2. Yeah? And we get 85.73. Afterwards, we did 85.743 divided by 100, and we got this. This is what we call our iodine value. And essentially, the higher the iodine value, the higher the degree of saturation of this compound. Yeah? Does that make sense to everyone? Okay. Salam, it makes sense. This is like basically the only new thing that you guys have done. Emeth, Kavinu, does that make sense for the two of you? So, keep going forward. So it says here, calculate the number of carbon-carbon double bonds in linolenic acid. So obviously we can look in the data book, but it wants us to calculate it using these. Yeah. So here we're going to do 7.6 divided by 53.6. So we do here 7.6 divided by 53.6. And this finds us the number of moles of iodine. So here we have here 7.6 divided by 253.6. We get here 0.029 ... right? Then we're going to find out the number of moles of oleic acid, of linolenic acid, which has a molar mass of 797. So we do here 2.7 divided by 789. So here we do 2.7 divided by 789. We get here 0.009 ... And here we want to determine the ratio between these two. So we're going to do 0.029 ... divided by 0.009 ... And here, if we do that, we should get approximately 3, which means here there's a 3-to-1 ratio. There's 3 iodines for 1 linolenic acid. Linolenic acid, which means here that there are 3 carbon-carbon double bonds in 1 linolenic acid. Does that make sense for everyone? All good, perfect. Oh, makes sense for Salam, it makes sense for Swayam, for that Kavinu, Imeth, Joe, Blessing. What do you guys think? Okay, perfect. So, I'll let you guys have a go at this one. What is, if an oil, 18.8 grams of an oil reacts with 11.3 grams of iodine, what is the iodine value? Remember, iodine value is just the mass of iodine divided by 100 grams of the oil or fat. Yeah? So what do you guys think it is? So what do you guys think? A, B, C, or D? One person saying C, A, C. So this is C. The answer here is C. You do here 11.3 divided by 18.8 to find out how much reacts with 1 gram, and then you can times this one by 100 to find out how much reacts with 100 grams. So, and here we've gotten to the end of this one. So, that is the chemical analysis section of organic chemistry. Yeah? We have 2 more sections that we need to deal with. Probably one of the bigger ones, which will be the what's the word called? Instrumental analysis. And then the very last thing we do is medicinal chemistry. And then you guys are basically done with chemistry for the year, or the majority of you guys are done. You have maybe rates you need to do, electrolysis for some of you, but besides that, or if you're Swayam, you'll be doing galvanic cells. No shade towards you. It's just I don't know what the hell the school's doing, but anyway. So I'm having a stroke. Does anyone have any questions about this? So I have nothing else to add for this. We got through the content, right? Can we watch Invincible? Dude, I'm watching it. I swear I'm watching it. Can we watch JJ? Dude, those are 2 good shows. But if you guys don't have any questions, I'm gonna stop the recording here.